to the ion beam. So the ions were always coming in at grazing incidence to every surface on this triangle, all three of them. And so we expect the cleanliness of this triangular surface to be similar to the rectangular one. And so this is really suggestive of this arc-like termination because it relies on some kind of phase coherence of the thickness of my sample. And another kind of more detailed effect that we expect of these kind of non-local Fermi arc-like quantum oscillations is that as the electron slides along the surface arc, it doesn't actually reach the end of the arc before it jumps into the bulk. But if you look at kind of non-adiabatic corrections to this semi-classical picture, you find that the electron actually jumps into the bulk when it reaches, say, an inverse magnetic length of the surface. So actually the arc length that you have to slide across depends on field and becomes shorter and shorter as you go to stronger and stronger fields. And what this means is that actually the position of these peaks is not regularly spaced with Landau level index, but kind of slides down as you go to larger Landau level index. And here you can see the measure agrees reasonably well with this non-adiabatic correction, where this coefficient is, say, roughly of order 1. This 4 is because you have 4 order of these if you go around. And what it turns into if you Fourier transform this is that the line shape for the surface peak, so this is a theoretical calculation, gets kind of smushed over towards low frequencies. So it's not a sharp Lorentzian line shape like you would expect from normal quantum oscillations, but this very asymmetric peak. And indeed, that's what they see in the data. And it agrees remarkably well with this kind of shape you expect here. And I want to comment that you can also get strange line shapes from, say, precursors to spin splitting. Say if this were a conventional or topological insulator-like surface. But actually, these have the wrong sign of correction. Those would bend up in this plot. And they would also, the magnitude is unphysically large. It would require some huge G factors. That's kind of several hundred. And also, it wouldn't produce this kind of sharply asymmetric line shape because you would roughly have the two frequencies, one for the spin up and one for the spin down. That kind of pulls the peak apart as you go to higher fields. So that would be a more symmetric broadening. All right, so there's a lot of information. So let me just summarize what's seen and what's not seen in these cadmium arsenide microstructures relative to what we expect. So we see the surface component of the quantum oscillations only in thin films, which is consistent with these kind of orbits that require going through the bulk. And there's some reasonable agreements with the theoretical dependence on disorder and what's observed. More observation of the oscillations require parallel so having surfaces that are at an angle with each other or similar oscillations. Someone has basically depended on the length of the bulk. Another thing, if you remember, we predicted that if you go to too large of fields, there's a field at which the quantum oscillations stop. This is actually not observed over the field range that's accessible right now. And if you do kind of back of the envelope estimate, you expect these saturation fields to be few Tesla. So it's a little troublesome, but it's possible that they're kind of lurking just beyond the field range probe. But this is something that needs further study. And there's also clearly a surface base based on the angle dependence. And in the first part of my talk, I mentioned that if you look carefully at the angle dependence of these peaks, you can actually back off the fact that there's a thickness-dependent peak. It's really kind of like a way to measure this topological connection of surface and bulk. So unfortunately, doing this is kind of complicated in this setup. And the reason is, well, there's several reasons. The first is that the surface and the bulk contributions come at very similar frequencies. So positions of these peaks are kind of all on top of each other. So, and the other thing is that this line shape of the surface component kind of bleeds into the bulk, so it's hard to kind of disentangle them. So we were unable to cleanly distinguish them at this point. Basically, the error bars in the position of the peak is larger than their separations. Okay, so maybe let me just skip this summary slide and finish with just a brief advertisement. So far I've been talking about magnetic signatures of this topological features in wire interact semi-metals. There's also high field measurements provide a simple kind of way to diagnose a wild semi-metal. And the reason is that, so here, looking at torque magnetometry measurements, basically a measurement of magnetization, or rather magnetization anisotropy. And wild electrons are kind of special in that you have this lowest chiral Landau level. And so as I crank up the field, if I start with some finite doping, all the states are increasingly piled into this lowest Landau level. So the energy of the conduction states are actually decreasing as I crank up the magnetic field, which gives me a paramagnetic response to magnetic field. And once I'm in this quantum limit, the energy stops depending on field, because this lowest Landau level doesn't depend on field. And then what's left is any residual diamagnetism from these valence bands or from some of these materials that have kind of conduction, massive conduction pockets also. So what you would expect in torque for the wild semi-metal is a big reversal in torque. First you kind of this paramagnetic thing, and then when you reach the quantum limit, it kind of turns around and you just get some diamagnetism from the background. Whereas for conventional electrons, you expect it to kind of go up and maybe just by some quantum oscillations and just get diamagnetism the whole way. And indeed, if you measure this in naive marsenite, which is one of these wild candidates, you see exactly this kind of torque reversal. So this may be a simple symptom to diagnose a wild semi-metal. All right, so thanks a lot for your attention.
Questions?
This might not be completely fair. It might be more appropriate for your experimental colleagues, but a couple of times you mentioned how clean the surfaces were from the focused ion beam, and I was wondering a couple of things. One is how was that quantified? And secondly, kind of what's at stake? How sensitive are these sorts of effects to weak disorder that's almost certainly at the surface, even despite these efforts?
Right. So I have a kind of indirect answer, which is that since you're seeing some surface component of the quantum oscillations, you know that at least the portion of the orbit that's on the surface is clean enough that you can complete it without scattering. And so since you see these nice clean quantum oscillations, it's indicative of having a very clean surface. So yeah, okay, it's hard to extract, say, what's exactly the transport, what mean free path of the surface, since the bulk is also conducting. But I think there's a really good sign that the surfaces are morally clean in the sense that cyclotron frequency times the scattering rate is large, at a few Tesla.
I was curious if your collaborators had done some sort of characterization of the surfaces.
Yeah, I believe they have, but I can't speak to the details. I mean, they know how thick the ion implantation layers are and things like that. So,
thank you.
I have a question. So I'm having a bit of a difficulty really understanding when you tilt the field, how does this bulk transport work? Because it seems that once you tilt the field in real space, the electron moves at an angle. Right?
Yeah, precisely.
So does that affect the outcome in any way?
Yeah, so the chiral Landau level goes along the magnetic field, just as you say. And so if I tilt the field relative to the surface, it has to go further through the bulk. And so actually you expect the scattering to become more and more detrimental the longer you make this orbit. And indeed, actually, they see that as they tilt the surface, the amplitude, the magnetic field, the amplitude of the surface oscillation dies pretty quickly. So it's only observable within some, 30 degrees of the top surface. So it's kind of consistent with what you expect.
Other questions?